Good morning. It is 9 o'clock Central Standard Time. This is March the 2nd, 2021. And the weather out here in north central Texas, at Seagoville, Texas, it's sunny and cool, but looks like it's going to be a wonderful day. We want to say a very special welcome to H.I. Holland Prep from Dallas ISD for joining us, the students and the teacher for joining us this morning. We hope you enjoy program and learn from it. If you're watching and you have not signed up, please go to www.tinycc/EEC register and sign up for it. This is just for our attendance records. This morning, we're going to do a program called Sun, Earth, and Moon. During this virtual field trip, students will discover that there are recognizable patterns in the natural world and among the Sun, Earth, and Moon systems. Students will compare the physical characteristics of the Sun, Earth, and Moon and explore the day-night cycle seasons and the lunar cycle. Ms. Ramirez will do a program called Day and Night. Mr. Monroe will introduce you to the seasons. Ms. Fuller will cover the lunar cycle, and Ms. Nash will cover physical characteristics of the Sun, Earth, and the Moon. You cannot verbally ask us a question, but you can go online and go to www.tiny.cc/EEC /question/answer and send us in your questions pertaining to the program. We'll do our best to answer them in the program, but if not, we'll send the answer to the teacher. Now I'm going to stop sharing my screen. And Ms. Fuller is going to tell you, and Ms. Ramirez, I'm sorry, is going to tell you all about day and night.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about day and night cycles. So I'm going to go ahead and share my screen with you guys, and then we'll start our presentation. It's just a super quick PowerPoint, and then we'll do some actual demonstrations. So let me get our presentation started. And I just have a couple of questions for you guys. My first question is, what are objects that you might see in the daytime sky? And then think about what are some things you might see in the nighttime sky? And if I were to ask you guys to draw a picture of the day sky and a picture of the night sky, what would it look like? And think about what are some patterns that you notice as the day progresses. So if you would like, you can take a moment to pause the video for discussion and allow time to draw your pictures, but I'm going to go ahead and show you some examples of what we see during the day versus what we see at night. So if we take a look at our little picture here, typically, when we think of the daytime, we think of the bright, shining sun. And typically, when we think of the nighttime, we think of the moon and the stars. However, not a lot of people are aware that the moon and the stars are there even during the daytime. We just don't see them that well because the sun is so bright, it's drowning the other objects out. So during the nighttime, our moon is actually reflecting back light from the sun. So the moon doesn't actually produce its own light, it's just reflecting that sunlight back. So as we go through our presentation today, our essential question is what causes day and night? And hopefully by the end of this presentation, you'll be able to explain what causes that. So keep that in mind so that you can answer that by the end of this segment. So what we're going to look at now is just a quick little video that helps us understand the apparent motion or movement of our sun across the sky. So you guys are going to watch this video and make some observations. What are you guys noticing? Think about what you see in the diagram as far as the labels and the apparent motion of the sun. Now think about, is the sun really moving or what's really going on here? So as the sun goes around for the second time, we'll notice that the sun is appearing to rise in the east and set in the west. Now we call it the apparent motion because it's not really moving. Instead, as we can see in the video, the earth is the one that is moving. The earth is actually rotating or spinning around an axis. So let's watch that video one more time and we'll go over, went too much forward. We'll go over what you guys saw. So we'll see the sun appears to be rising in the east. So here we are at the east. At noon, the sun's going to be highest in the sky. And then 6 hours later, the sun will appear to set in the west. And we know this whole process takes 24 hours or 1 day. And again, as you can see from the video, we know that it's not the sun that's moving. Instead, it's our own planet that is rotating or spinning around an axis, and that is what is giving the appearance that the sun is moving. And that's why we call it the apparent motion. It looks like the sun is moving, but it's really not. So in our next little video, this is a cool video from Texas A&M. They have what's called a Foucault pendulum at their physics building, and you can look this up on YouTube. But my challenge question for you guys is to explain how Foucault's pendulum proves that the Earth rotates. And this is a cool pendulum. It's 7 stories tall, so it's really tall, and it's over 400 pounds. So as you watch this video on your own time, see if you can use this video to help you explain how Foucault was able to prove that the Earth actually rotates. So I'm going to stop our screen share, and we're going to do a quick little demonstration. So here I have a lantern, and it's going to represent the sun. And here, of course, I have our Earth, and this globe is again representing planet Earth. So in our model, think about what are some things that you notice about our model, and also think about what are some limitations of our model. And when I say a limitation, I'm talking about what are some things that might be problems in my model that might not totally be accurate. So when we talk about limitations, the first thing I noticed is my distances between these objects are not to scale, but also my sizes are not to scale and they're not accurate. So we know in real life, the sun is massive. It is so much larger than planet Earth. And to put that into perspective, if you take a look at your classroom door, or if you're at home, take a look at your bedroom door. If the sun were the size of a doorway, then planet Earth would only be the size of a dime. So that is just how massive the sun is compared to our much smaller planet Earth. So those are a couple of limitations with my model that I'm using today. So just be aware of that. So we're going to model Earth's rotation. So let's take a look at our globe here. We have an axis, and in my model, my axis is just the stick that I have here. An axis is just an imaginary line through which a planetary body will rotate around. Now, we know that the Earth is actually tilted at about 23.5 degrees about that axis. And we also know that the Earth rotates or spins, and it actually spins counterclockwise. So when I say counterclockwise, here's an example of a clock. Counterclockwise just means the opposite direction of a clock. So if we look at our clock, the opposite direction would be this way. So that's what we mean by counterclockwise. And the way that I remember counterclockwise, I went to A&M and we always say gig 'em Aggies. Gig 'em Aggies is just a thumbs up sign, and we usually use our right arm or our right hand. So if you take your right arm and do a thumbs up, look at the direction your fingers are moving toward. That is counterclockwise. So that's a good way to help you guys remember the direction that the Earth is rotating or spinning. If you just look at the direction your thumbs are going. So let's take a look at our model in motion. So we know that we live in Dallas, Texas, which is over here in this orange dot in North America. And I'm going to start our model in this position right here. So right now we have Dallas, Texas right here, and here's our sun. So is this modeling day or night for Dallas, Texas? And then why do you think that? So hopefully you guys said it would be modeling daytime for Dallas, Texas. So this half of the globe would be experiencing day. What about the other half of the globe on this side? So they would be experiencing nighttime. Now we're back here on Dallas, Texas. This is going to be representing noon when the sun is highest in the sky. Now we know that the Earth is going to rotate counterclockwise. So we're going to rotate planet Earth, and eventually Earth is going to come, or Dallas is going to come to this point right over here. So 6 hours later, where we are in Dallas, Texas, we'll be experiencing sunset. And we know that the sun sets in the west. The Earth is going to continue rotating counterclockwise. Eventually, where we are in Dallas, Texas, will be on this side of the globe, and Dallas, Texas will be experiencing midnight. The Earth is going to continue rotating another 6 more hours. Eventually, where we are in Dallas, Texas, it's going to be experiencing sunrise. And that sunrise will appear to rise from the east. And then the Earth is going to continue rotating counterclockwise. And here we are again, Dallas, Texas is back at noon. So we have noon when the sun is highest in the sky. We have sunset in the west. We have midnight. And then we have sunrise in the east. And we're back to our 24-hour cycle. So we know that it takes 1 day or 24 hours for this Earth to complete one rotation. Now, when we did our modeling, did the sun move at all? So hopefully you answered no. So it was actually the Earth that was rotating or spinning around its axis. Now, it is important to note that the sun does rotate. So the sun is also rotating around its own axis, just like the Earth is rotating, but the sun is not going around. So the sun's not actually moving around. So it's the Earth's rotation that causes day and night and the sun appearing to set and rise. So we're going to do really quickly a little poem to help us remember rotation. So if you would like, you can stand up with me and repeat after me. We're going to represent the Earth. I have my sun over here. If you will just take a finger to represent your axis, we're going to put it on top of us. We are tilted at 23.5 degrees, and we are going to rotate or spin counterclockwise. And if you need help with remembering what direction you're spinning, do your right hand, put a thumbs up, look at the direction your fingers are going, and that's going to tell you which way you're spinning. So you guys are going to repeat after me. Rotation, rotation, let's talk about rotation. And one more time. Rotation, rotation, let's talk about rotation. Causes day and night, causes day and night, and the sun going across the sky, and the sun going across the sky. So rotation, or that spinning motion, causes day and night, and the sun appearing to move across the sky. In your next segment, you're going to learn another R word, and a lot of students get those words confused. So in this segment, we learned about rotation, and that causes day and night. The way I remember it is rotation has an A, just like day. And then the other R word you're going to learn here in a second, and that's revolve, and it means something totally different. So just keep that in mind. And that is all I have for you guys today for rotation, which is the spinning of the Earth. And we're going to go ahead and pass it back to Dr. Gorman, and he's going to answer any questions.
Thank you, Ms. Ramirez. And we did have a question from Durian at Holland, and it says, what are we going to do for our field trip today? Well, since you can't come out here and do a normal field trip with the animals and nature and everything, we're going to do a program called Characteristics of the Systems of the Sun, the Moon, and the Earth. Hopefully, we're going to reinforce what your teacher has taught you or will teach you in the classroom. We hope you enjoy it, but when this mess is over, then influence your teacher to come out here on a regular field trip, and we'll be able to compare the two. All right, now, Mr. Monroe, I'm getting these teachers all mixed up this morning, sorry. Mr. Monroe is going to talk to you about the seasons.
Good morning, students. My name is Mr. Monroe, and we're going to be looking at or exploring seasons and why we have seasons. And to do that, we're going to be looking closely at the relationship that our planet, the planet Earth, has with the sun. Now, Ms. Ramirez talked about night and day. And again, that's a relationship of motion and movement that our planet, the planet Earth, has with the sun. And the motion that gives you night and day, you heard her say, is the rotation of our planet, the spinning of our planet. And with me, we're going to be using another R word called revolving or revolution, meaning that, again, it's a focus on the movement of our planet in relationship with the sun. Now, I'm not going to go any further with the model yet. What I'm going to do is go over a short PowerPoint with you all so that you can get a better understanding of why we have seasons. So bear with me just for a minute here while I share my screen. Why do we have seasons? Well, that's what we're going to be looking at and investigating so you guys can get a better understanding. Well, old PowerPoint doesn't really want to work today. Wonder what's going on with that. Here we go. The Earth rotates on its axis in an imaginary vertical line around which the planet Earth spins every 23 hours and 56 minutes. And that is equivalent to basically what we call one day, and that's the rotation of the Earth. One day on Earth is when our side of the Earth faces the sun. Night on Earth is when the side of the Earth, and Miss Ramirez explained this to you, we are on facing away from the sun, okay? Now, when we talk about revolution, we're talking about moving around the sun, orbiting the sun like a satellite. And it takes the Earth 365.25 days to travel or revolve around the sun once. This is called a year. Now, basically, you're familiar with 365 days being a year. But if you look, we have a little bit left over, don't we? 0.25 hundredths of a day, which is equivalent to 1/4 of a day. And you know, eventually that adds up. There was a great emperor, I guess, long ago, who was the emperor of the Roman Empire. And Julius Caesar was his name, and he realized that our people around him in his leadership roles, they realized that, and basically they came up with every 4 years they would add a day to the year. And so basically later on, someone else kind of picked up the idea, and he was a pope, Pope Gregory the 13th, and he came up with a calendar called the Gregorian Calendar. And what happened was he created what we call the leap year. And the leap year happens every 4 years. And what that means is there's a month, in fact, it is the month of February, that every 4 years there's an added day added to that month. The last time it happened was in the year of 2020. The month of February had 29 days. We are now in the year of 2021. And if you notice, we've already had the month of February come to an end, and it ended with 28 days. Now, this won't happen again. We will not have a leap year until the year 2024. And at that time, if you look at the calendar, February will have 29 days. If you look at this image here, you can see the tilt of the image of our planet is at an angle. And Ms. Ramirez told you that that angle was 23.5 degrees. And it stays at that angle. It doesn't revert or increase the angle or decrease the angle. It stays at 23.5 degrees. Now, that axis is that imaginary line that goes right through the center of our planet. And of course, right here, we see that that axis is straight up and down, north and south, but it's leaning. And so our planet has a mean lean to it. Now, again, a rotation, remember, that's to spin on its axis. A revolution is the motion of the body around another body. Orbit is the path that is followed around another body in space. And you know what? Our planet, the planet Earth, orbits around the sun. It's not orbiting around the sun in a perfect circle. It's what we call an ellipse. Seasons are not caused by how close the Earth is to the sun. In fact, The Earth is closest to the sun around January the 3rd and furthest away from the sun on July or around July the 4th. And if you really think about it, if you're really closest to the sun, I guess you should have the season of summer. But look what it's saying, January the 3rd. Well, that's the season of winter, isn't it? And July the 4th, guess what? It's the furthest away from the sun, and that's the season of summer. So it really doesn't have anything to do with how far or how close you are to the sun, okay? Seasons are the result of the tilt of the Earth's axis. The Earth's axis is tilted again at 23.5 degrees. This tilting is why we have seasons like fall, winter, spring, and summer. The number of daylight hours is greater for the hemisphere or half of the Earth that is tilted toward the sun. Now, if we look at these images here, the season of winter, we see that here the United States is tilted away from the sun. So at that time, guess what? We're having the season of winter. In spring, we start beginning to tilt back toward the sun. And we're getting a little more of the sun's direct heat and light energy. So the air tends to be a little warmer and we're getting more sunlight and the days are beginning to get a little longer. And so during the spring, we're getting our conditions where things may start growing and getting ready for the spring season or summer season. Here we have summer, and as we look at this, we're really leaning toward the sun. And that means our days are going to get longer and we're going to get a lot more of the sun's light and heat energy, meaning that we're going to warm up pretty good during that season. And then we get into fall and we start leaning away from the sun's light and heat energy. Okay, so there you have it right there. That image shows that it's the tilt of the axis, our axis, the tilt of our planet that causes the seasons. Summer is warmer than winter in each hemisphere because the sun's rays hit the Earth at a more direct angle during summer than during the winter. And we can see that in this image. Also, the days are much longer than the nights during the summer. During the winter, the sun's rays hit the Earth at an extreme angle, and the days are very short. These effects are due to the tilt of the Earth's axis. And I know you guys noticed that when winter comes, it probably gets dark somewhere between 5 and 6 p.m. in the evening. We don't have much daylight, do we? And again, if we look at these images here, sun, during the summer, we're getting a lot of the sun's direct sunlight and heat energy. More sunlight on the northern hemisphere of the United States. The continental United States is located above the equator, so that means that we're in the northern hemisphere. And if we're leaning toward the the sun, what do you think's happening down here below? Well, while we're having summer, what do you think they're having? Because they're tilting away. They're probably having winter, okay? Now, looking at this image, more sunlight is on the southern hemisphere. So the tilt here is closest to the sun's hot heat and, I lost that. Heat and light energy. And basically they're having summer, and guess what we're having? We're having winter. Isn't that something? Solstices. Solstices occur twice a year when the tilt of the Earth's axis is oriented at its extremes, meaning it's tilted the furthest or the closest. That is usually when the solstice happens. Winter solstices, it's the shortest day of the year. In the northern hemisphere, it occurs on December the 21st or the 22nd and marks the beginning of the season of winter. The summer solstice is the longest day of the year. It occurs on June the 20th or June the 21st and marks the beginning of summer. And the really amazing thing about that is after that solstice happens, if you calculate, let's say the summer solstice happens, after that happens, then our days start getting a little shorter as we inch closer and closer to winter. We're going to skip this. You'll study that a little later on. But another word that I want you to become familiar with is equinoxes. Equinoxes are days that last, a day lasts 12 hours and a night lasts 12 hours. So we have an equal amount of day and an equal amount of night that makes up the full day, 12 and 12. Equinox literally means equal night. Sunlight strikes the earth most directly at the equator. This occurs twice a year. The vernal equinox happens in the spring, and it usually happens March the 20th, okay? So that's coming up. And want you guys to kind of observe that on March the 20th, guess what? There'll be 12 hours of daylight and 12 hours of night. And the autumn equinox usually happens September the 22nd or the 23rd. The Earth's seasons are not caused by the differences in the distance from the sun throughout the year. And that is the big science idea that is not very factual, is it? Now, students, I'm going to stop sharing my screen. I'm about to run out of time. I want to look at this model one more time, and I'm going to try to make it work for you where you guys can see. Right now, I have marked an X on the continental USA. And we're going to start our rotation where the planet is spinning and the revolving. And you can see that as we move, the X is away from the sun. It's moving away from the sun. So that puts us in the season of winter. And as we move around, remember, it takes 365 days for this to happen, to go completely around. So we can see the tilt changing. We're kind of at an angle that is not directly, and I'll move this over so you can see, not directly, but it's still kind of leaning away, okay? So again, it's the tilt of our axis, on our axis, that creates our seasons. Now, students, I've run out of time, so what I'm going to do, I'm going to turn it back over to Dr. Gorman. And if any of you have any questions, I'm sure he can answer them for you.
Thank you, Mr. Monroe. And yes, we definitely had a question, and it was a very important question. What is your favorite season? And earlier, I had reported that due to a Gallup poll, that the spring was the most favorite season. I did a little more research on that, which is the lesson I want you to learn. Don't just take the first thing. If you have the opportunity, do 2 or 3 different researches on your questions. A little more research come up with the idea that it depends on what part of the United States you live in. If you live up in the cold north, say Minnesota, New York, Maine, something like that, then spring is your favorite season. You're looking forward to it warming up from that cold winter. If you live down here in the South, where we have these brutally hot summers, then fall is your favorite season. You're looking for a little cool weather after them more 100-degree days in August and sometime in September. And now Miss Fuller is going to introduce you to the lunar cycle.
Good morning, this March 2nd, Texas Independence Day. My name is Mrs. Fuller, and this is my lab assistant. This is Jamie. Now, when you look at the moon, the full moon, like we had on Saturday, February 27th, what do you see? Do you see an image in the full moon? Some people see rabbits, some people see a dragon, all different kinds of things. Do you see a guinea pig in the moon? I'm going to put Jamie down with some lettuce. And I'm going to share my screen with you. And let's look at all the different ideas we have about the lunar cycle. So, phases of the moon, the lunar cycle. Now, we have a quote here from the play Romeo and Juliet. Oh, swear not by the moon, the inconstant moon, who monthly changes in her circled orb, lest that thy love likewise be variable. Now, Juliet in this play recognizes the fact that the moon changes every night. It never stays the same in the way that we see it. So she was saying she didn't want Romeo to pledge his love to something that was constantly changing. So when you look in the moon, in a lot of people, when they look at the moon, they see a man in the moon. What do you see in the moon? A dragon, a dog, a buffalo, a woman, a rabbit? Now, there are two groups of people on opposite sides of the planet, the cultures in the Chinese country and then all in China, and then also the Anasazi Indians in the American Southwest. They saw this as the face of the rabbit. These is the two front legs of the rabbit. This the body of the rabbit. This as the ears of the rabbit. And these the two hind legs of the rabbit, and following behind the little puffy tail of the rabbit. Well, since someone taught me that, I can't look at the moon and see anything but a rabbit. Now, does the moon rotate? This is a big question also. This puts these two ideas, the one about rotation from Ms. Ramirez and revolution from Mr. Monroe, together. And the answer is the moon rotates and revolves at the same time, 29.5 days. The moon spins once a month as it circles the earth. That's why we only see one side of the moon. This is called a synchronous rotation, which means it's synchronized with its revolution. It's tidally locked as it revolves around the earth, and the earth is tilted on its axis at 23.5 degrees, like Mr. Monroe pointed out. But a lot of people don't realize the moon is also tilted on its axis, but not that much, only about 5 degrees. Now, the 6 images you see at the bottom of this slide are different phases of the moon. And if you see the phase where the dark portion is on the left-hand side, that is a waxing phase. And if you see it where the dark portion's on the right-hand side, that's a waning phase. Waxing means growing larger, and waning means growing smaller. Now I'm going to show you a real short video, and I want you to keep your eye on this portion. This is called the Terminator. Just like in that movie with Arnold Schwarzenegger. Well, what this is it's the line between dark and light. Now remember, the moon doesn't have any light of its own. It's illuminated by the light of the sun. It simply reflects that to us. So what we have right here is a waxing gibbous. So we're going to watch this go. And that's the new moon. Now we've got a crescent, a waxing crescent, a first quarter, waxing gibbous, full moon, and now it starts over again. I'm going to go one more time. New moon, crescent, waxing crescent, first quarter, waxing gibbous, full moon, and then off we go. So let's go right here. This is our next slide. This shows the different phases of the moon like you just saw illustrated in the video from NASA. So right here is the new moon. You can't see it because it has no illumination. And then we go toward the full moon. So we have a waxing crescent, first quarter, waxing gibbous, full moon. This is what we saw on Saturday. I went outside on my deck like 3 times to find it, but of course the sky was overcast. We were getting rain. There's our waning. Waning means to grow smaller. Waning gibbous, third quarter, waning crescent, and then the new moon again. Now, it looks like we have, I'm having technical difficulties here. So let's see if we can skip down past that video. And we're going to look at the new moon. And you can't see it because it's not illuminated. It appears to be totally dark. It rises and sets with the sun and crosses the ecliptic with the sun. The ecliptic's that line in the sky that the sun crosses, the moon crosses, and the planets at night. Well, they're during the day too, but we can't see it. So it represents, now this represents the first stage of the lunar cycle. Now, what does gibbous mean? It comes from a word meaning humpback. And this is the one that appears to be more than a circle, but less than a semicircle. And this one over here is a waxing gibbous, and this one over here is a waning gibbous. What's a crescent moon? That's the one, a waxing crescent can be seen in the western sky a day or so after the new moon. It slips below the horizon with the sun. Waxing means growing. A waning crescent can be seen in the eastern sky before dawn. Waning means getting smaller. This one used to be called the old moon. First quarter, the first quarter is not talking about the amount of light, the amount of illumination on the moon. It's talking about, it's the moon. It looks like it's half of a moon. That's the first quarter. And then when it comes around the other side, third quarter. Now, I want to talk very briefly about women in science. This is Mary Jackson. She was an aerospace engineer at NASA, and she worked on the Apollo 11 space launch to the moon. So she helped put astronauts on the moon. Now, here's a challenge for you. Observe the moon every night for 2 months and record your observation in your science notebook every day. What did you see? Okay, so let's get out of this. I want to show you a real quick demonstration, and then I'll turn you back over to Mr. Gorman. This is really easy to do. You can get a styrofoam ball and put it on a sharp pencil. I just took a golf ball and taped it onto a golf tee, and my head represents the earth, and I've got a real bright light right in front of me. So if I put it right here, you see it completely illuminated, but I'm the earth. So what do I see? Nothing. It looks completely dark. And as it goes around, I start seeing a crescent, then first quarter, then gibbous, and then back here, we've got the full moon. And then it's going to start waning. The illuminated part's going to start to wane. So I get here, third quarter, gibbous, yes, and crescent, and then we get back to the new moon. So the moon is fascinating, and I hope you have a good time learning about the moon. Dr. Gorman will answer any questions you have. Thank you.
Thank you, Ms. Fuller. We did have a question from Heidi. She said, why, if the earth is moving so fast, why can't we feel it? And the answer to that is because we're moving at the same speed that the earth is. Now, if the earth came to a sudden stop, now you got to realize at the equator, the earth is moving about 1,000 miles an hour, and you are too. If the earth came to a sudden stop and you didn't, what would happen? You would continue on at 1,000 miles an hour until gravity or friction slowed you down, or a mountain or something that you smashed into at 600 or 700 or 800 miles an hour. So if the moon stopped, everything would continue. Big rocks, cars, everything that wasn't tied down would continue to go. And now we're going to hear Miss Nash tell us about characteristics of the sun, the earth, and the moon.
Hello, very quickly, the physical characteristics. So what I was thinking of is differences and commonalities. In other words, things I have in common and differences. So we can think of lots of differences, things like size. Of course, the sun is gigantic, the moon is tiny, and the earth is not very big either. What are they made of? The composition. So the sun is made of mostly hydrogen with some helium. The earth is rock with also gas and water on it. And the moon is just rock. Does it have life? Only us. We humans have gone to the moon, but we can't stay there and really live there. So let's look at a couple of pictures really quickly, since we can't really go to the sun or the moon, at least not today. There we go. And really quickly. So I like this one because it has all three of our parts of our solar system. So we do have one thing in common. We're all part of the solar system. That means that we on planet Earth revolve, orbit the sun, and the moon orbits us. Okay. And the sun, of course, is the center of that solar system. And we're all bound by gravity. We all have gravity. Gravity keeps the Earth revolving around the sun. Gravity keeps the moon revolving around the Earth. We all have gravity. Everything that has mass has gravity. The sun has a lot of gravity because it's so big. The Earth has less and the moon has even less. The moon's gravity does affect us on Earth through the tides. So here we have the sun going down or coming up, and over here the moon, and here our wonderful planet Earth. Here we have the Earth with the moon, and you can see that part of it is illuminated. The sun is over on the other side of the Earth. Here's our sun, a medium-sized star. Okay, we can't walk around like we would burn up. It's not solid. It produces light and heat energy that we use on planet Earth. Our atmosphere traps that heat, and plants use the light energy. So the moon is made of rock marked by craters. It reflects light. It doesn't have its own light. And the thing I like about this picture down here is you can see that we on planet Earth are also reflecting light. Okay? So from the moon, we see the Earth reflecting light. And other planets, of course, do the same thing. That's why we see Venus and we call her the morning star. Venus is not a star, it's just reflecting light from the sun. And of course, the moon has no atmosphere, so the heat energy from the sun is not trapped. It just goes back out into outer space, and it's very cold. So our Earth is rocks, gases, and liquid. It supports life, and we need to help support our planet and all the other creatures that share it. Okay, so really quickly, in the 2 minutes I have left, let's imagine this is our sun. Okay, it would actually be quite a bit larger than this. And we imagine this is our planet Earth. Okay. Our planet Earth, and then our tiny moon. Okay. So let me make yourself a chart to compare these sun, Earth, and moon on things like size, composition, other how far away they are from each other, things like that. And the thing to remember is that our planet is the only one with life, and our little friends here, Squeaky, the gecko, says, take good care of planet Earth. So thank you, and Dr. Gorman will answer any questions.
Thank you, Ms. Nash. And we did have a question from, let's see, Eric at Holland. And why are seasons important? And I'm going to give you the book answer instead of what I think. Climate, weather, and the change of the seasons affect much of what we do each day. Many people choose where to live based on the climate, and weather can be both a helpful, destructive force for people or their property. As we just found that out, and a lot of you probably may either live in a house that had busted pipes, or you may have a neighbor or a friend that had a lot. I lost a lot of trees, I think, a lot of shrubbery. That was about the only major damage I had. But the change of the seasons allows for many different types of work, food, celebrations, and recreation. So a lot of times we live in an area that has warmer climate or warmer seasons. Thank you, Eric. And now I'm going to share my screen. During this field trip, students discovered that there are recognizable patterns in the natural world and among the sun, earth, and moon system. Students compared the physical characteristics of the sun, earth, and moon and explored the day-night cycle, seasons, and the lunar cycle. Ms. Ramirez discussed day and night. Mr. Monroe told you about the seasons. Ms. Fuller explained the lunar cycle, and Ms. Nash covered physical characteristics of the earth and the moon. Thank you. How did we do? Teachers, if you would, fill out a form, www.tiny.cc/EEC feedback, and send it to us. It's a very brief form, but we would appreciate you doing that. All right, you guys have a wonderful day, but most importantly, have a great life. Thank you for joining us. Hope to see you whenever we get back to the regular field trips.